All right, in this lesson, we're going to be looking at simple compound circuits. Now, when I say simple compound circuit is just a circuit that has components that are in series and parallel. And so I'm just using as few components as possible on these to keep them relatively simple. That's why I say simple compound circuits. So if we look at this one, we can see that we've got this R1 that's in series with the power source, and it's in series with these two resistors that are in parallel with each other. Okay, so the first thing I want to do is find the total resistance, and to find the total resistance, I will need to find the resistance of these two resistors in parallel. So I'm going to have 1 over Rp, and I use Rp for the resistance for the parallel branch, because this isn't RT because it's not the total resistance. And that equals 1 over 300 plus 1 over 100. So 1 over Rp equals 0.0133. Now to get the Rp, I take the inverse of that, or I take 1 divided by the 0.0133, and I get 75 ohms of resistance for the parallel circuit. Right. So now I can redraw this like it's a simple series circuit with two resistors. I've got a 500 ohm and a 75 ohm. Now to get my total resistance, in a series circuit, we just add our resistance together, and I get 575 ohms of resistance. Right? Now to get the total current, to get my amps, block out the I, I've got E over R, which is 9 over 575, which equals 0.01565 amps. Or we could put that down as 15.7 milliamps, rounded off. All right, so now I've got 9 volts. I've got 2 resistors, or I've got my total resistance, and I've got my total current. So now I'm going to find out how much of that voltage is used across that first resistor. Okay, so to get the voltage across that R1, I multiply my current times the resistance. So that's 0.0157 times 500, and that comes out to 7.85 volts. Now I want to find out how many volts are left over to go through my parallel branch of the circuit. So I'm going to take the 9 volts that I started with, minus the 7.8 volts that are being used on that first resistor, and that gives me 1.15 volts that's going across the two resistors that are in parallel. And remember, with the parallel circuits, the amount of voltage is the same on every path. So this is like having just a parallel circuit with 1.5 volt power supply. So I can get my amount of current going through that second resistor. I put I2, that should be I1. That's going to be the 1.15 divided by 300. And that gives me 3.8 milliamps, or 0.0038 amps. Then to go through that third resistor, I take the 1.15 divided by 100, and I get 11.5 milliamps. So now I know my total resistance, I know my total current, and I know my voltage drop across the first resistor, how much voltage is left for the parallel branch of the circuit, and how much current's going through each branch of the parallel circuit. All right, so let's take a look at another one. So again, the first thing I want to do is find the resistance across my parallel resistors. I would say R1 over RP equals 1 over 800 plus 1 over 550. All right, here we're going to take a look at how to use a calculator. Okay, so now we can look at this again as a simple series circuit with 2 resistors. Now to get my total resistance, I take my 325.9 plus my 200 ohm resistor, and I get 525.9 ohms of total resistance. All right, so now I can find the total current going through there. So my since I'm looking for my current, I cover up the I, that's E divided by R. So I'll take my 20 volts divided by 525.9.
I didn't understand that.
And that's going to equal 0.038 amps. And I'm going to go ahead and leave this as the 0.038. I could make that 38 milliamps, but since my calculations I'm using amps, I'm just going to go ahead and leave it as the 0.038. Now I want to find out how many volts I'm using across my 200 ohm resistor. Okay, so I'm just going to call that R1. So my voltage across R1 if I'm looking for the volts, I cover up the volts, it's just I times R. That's going to be 0.038 amps times my 200 ohms of resistance. And that's going to equal 7.6 volts. All right, so now let's add back our parallel branch to the circuit. And since I know that I'm dropping 7.6 volts across here, I'll take the 20 volts that I started with, so my voltage going across the parallel circuit is going to be my 20 minus 7.6, which is going to equal 12.4 volts. I'm going to change colors here because I don't care much for that pink. We'll try green, see how that looks. All right. So now we can just scribble out that resistor. We're just going to pretend like that's a straight wire there. And we've got a circuit with, that didn't work out too well either. So we've got a circuit with 12.4 volts. All right. So to find my current going across this first branch, whoops, let's see. Just want to erase that, not the whole thing. All right, since I'm looking for current, I cover up the I. It's E over R. So it's going to be the 12.4 divided by 800, which equals 0.0155, or we'd round that off to 0.016 amps. To find my current going through this second branch, again, the voltage stays the same. That's 12.4 divided by 550. That's going to give me 0.022545. So I'll go 0.0. Now we'll go 225. Okay, so now I know my total resistance. I know the resistance across my parallel circuits. I know how much current's going through each branch, and I know the voltage that's being dropped across that resistor. So that's all the information that we can get from that compound circuit. All right, so let's look at one more. So here we've got a 125 ohm resistor, 450 ohm, and a 775 ohm. Again, the first thing I want to do is find my total resistance across the parallel branch of the circuit. I'm going to say 1 over RP equals 1 over 450 plus 1 over 775. And again, you could just use your calculator and put it in the way I showed you on the last problem, or divide them out, get your decimals, and then take 1 divided by that. But either way, we're going to end up with 284.7 volts of resistance across the parallel branch of the circuit. Okay, so now we've narrowed it down to a simple series circuit, pretending like those two parallel resistors are just one resistor with a total resistance of 284.7. So now I can get my total resistance. So I'll say RT equals my 284.7 ohms of resistance plus the 125 ohms, which is going to give me a total of 409.7 ohms of resistance. So now I can find my total current. Again, I would just cover up the I. It'd be E divided by R. So that's going to be 12 divided by my 409.7. That's going to be 0.0293 amps. Right. So now I want to find out how many volts are being used with this first resistor. So my voltage across R1, again, if I'm looking for voltage, I cover up the E. It's I times R. That's going to be my 0.0293 times my resistance, which is 125 ohms. And that's going to be 3.7 volts. Now, if I want to find out how many volts are being dropped across here, I could use the same formula, or I can just subtract. So the voltage that's being used across the parallel circuit is going to be the 12 volts that I started with, minus the 3.7 volts that are being used across this resistor. And that's going to be 8.3 volts. All right, so let's bring back the parallel branch of the circuit. Now to find out how much current is going through this first branch, say I1 equals, now we're just going to pretend like that voltage isn't there, and this is just a straight wire across here without a resistor. And we've got an 8.3 volt DC power supply. All right, so if I cover up my I, it's E over R. That's going to be my 8.3 volts divided by 450. That equals 0.018, and then a 4 that repeats, amps. For my I2, I could take my 0.293 minus my 0.184 amps to get that, or I can take my 8.3 volts divided by my 775 ohms. That's going to equal 0.0107. And again, if we add these together, 4 plus 7, that's 11. That's going to be 9, 2. Okay. Now I've got 0.0293 here and 0.0291 here. And the reason we have a little bit of difference, and this is the 10,000th spot. Okay, so this is 10,000ths of 1. So we're going to be a little bit off here because we've rounded off on these. Because this both of my amps here are rounded off. My voltage is rounded off. So because of rounding errors, it's may not be exact to the 10,000th, but it's going to be pretty close. And so that gives us all the information we need to know about this circuit.